So let's do a review of what's going on right now. We've already covered camera ray generation and ray intersection routines, possible solutions and approach to these things. And I copied the code from our previous lessons to create a new shader called Shading Basics. So as you can see, this is what we have. It's still very hard to tell exactly what this is. It's basically just a 2D image. There's no sense of 3D in this thing because we're ignoring the fact that we're ignoring the details of how light will interact with the geometry, right? Based on the angle at which the light hits the surface, the intensity of the light that will bounce off that surface point is different, and there's things we can do with that to make it more realistic than it is right now. Right now, we only have the geometry, as I've said. Let's go over these steps for the basic direct ray tracing. First step is cast a ray. Second step is, intersect, which mainly performance problems and precision problems. And the third step is shade, which is the primary lesson of this video, which is what we're going to do. The fourth is let's just ignore the fourth step since it's really basic, really obvious what you should do here. After you finish shading, of course, you put the shaded color back into this main image. Okay, so how does shading work basically? If you recall, we're projecting rays out of the 2D image, which is going to be a grid of pixels, projecting out through a pixel, right? This intersection with the pixel hits some geometry at the point. Now realize that these pixels that you see on a screen are generally very small cells. Like we cannot even tell which. If you look very closely to any of the image on your screen, they are all in pixels. Mostly anti-aliased, but you should still be able to tell a little bit. But it's really, really small. So an approximation we can do is if we project the pixel out into a surface, into 3D, it's only going to take very, very, very small space. Right, and since we're rendering, any kind of geometry, it could be a sphere we're rendering. We don't know the curvature of the surface, but one good enough assumption is whatever curve they're rendering, if you zoom in close enough, right? If you zoom in close enough, it's always going to be approximately a flat surface. So since we're finding the shaded value or the color that's reflecting back to the viewer from a certain point, we know we can just reduce the complexity of the problem a little bit. Say we have some light source. Let's say we have a directional light source. Okay, what directional light source means? It's kind of like the sun. Whichever point on the Earth you're at, the sun always comes at you at the same direction because the sun and Earth are so far away. There's a really there's going to be some the sunlight are not emitted in parallel lines. It's emitted radially outwards, but when it hit the sun, all the light rays that the sun receives are approximately parallel to each other. So basically, if we have a surface and we have some predefined sun direction defined, this is our surface. Say we're shading this point, and we have a predefined direction of where the sun is coming into the point. All we need to do is how that light energy interact with the matter at this point, right? And say our viewer is looking here, looking from this direction. What is happening is that this light hits the surface. It has some interaction with it, can rescatter out from the surface, right? We can model it in different ways. The reason different materials appear differently to human eyes is because the distribution of the reflected light from the surface is different. And in this case, we can use, since we're just getting to the basics of shading, we can just start with a very simple model of how light works, which is diffuse shading. What it says is if light ray enters the matter, then it scatters a little bit, scatters completely stochastically, so it's completely a random process, and light, statistically speaking, it will have the same probability of exiting into every single possible direction. So it could exit here, 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 exit here, right? So a good process, again, this is, statistically speaking, it's going to radially, emit back out within the hemisphere. It's gonna, there's gonna be an equal amount of light, outgoing light, after the interaction ends, out through all the hemisphere points. I'm not gonna draw them out. So, obviously there's only one single light source in our case, we're assuming. So the light is coming this way. It's going to be distributed throughout the hemisphere. And we want to be physically based with these things. We want to be physically correct. So if there's only, say, 10 watts or something, all the outgoing light rays from this light source better be integrating to the 10 watts, because that's all the energy that's coming in. You cannot possibly have an outgoing, energy with the sum of more than 10 watts. By the way, watts is joule per second. It's at what rate the energy is coming in. And this is going to be the model for our light interaction. I don't want to go into too much detail into that. All I want to say is you want to watch out for these cases when you're modeling or making up your own light interaction scheme. So it turned out, if we have 1 over pi and integrate this over the hemisphere, what's the thing for hemisphere? I forgot. Whatever. Say this, I'm integrating 1 over pi over the entire hemisphere. This is a solid angle. Well, let's just forget this. We need the solid angle here to integrate all hemisphere, but let's just say, what is this value? This actually equates to 1, and we can use 1 over pi as the coefficient of how much of the light will radiate back out after interaction into our eye, because we're basically arbitrarily picking a ray that's exiting the surface, and that we can just say if the incoming sunlight is, say, x, and the receiver is going to see x over pi amount of energy, because 1 minus x over pi, which is the rest. No, it's x minus x over pi. This is the rest of the energy or emitting through all the other directions that the viewer cannot receive, because we're using a pinhole camera, and this is also how approximately the human eye works. So this is what we know. Basically, the light we see is the incoming sunlight divided by pi, and that's the amount of energy we see from the viewer. Well, if we do this, it'll still be flat, because sunlight, well, not really sunlight is. What I want to say is, after the light interaction, it will be the exitance. The light exitance divided by pi. And light exitance is whatever irradiance that's built up at the surface point due to the sunlight, right? However, if you do this light exitance, say it's if you treat it as a constant, then it's still gonna be flat, because there's gonna be a sign the same color. What you want to do, one critical perception that you need to make, or this is called the lambert law. Okay, very important. So say light comes in some direction, right? It's gonna be, since we're modeling a ray, we might as well just give it some, yeah. So say a sunlight ray is coming in, right? Of course, you cannot have literally a ray of 0 radius. So the width of the ray cannot be 0, physically speaking. So we'll give it some kind of, width, right? Since sunlight is completely parallel, the width of all the sunlight is going to be the same. So these are going to be photons. There's a certain density that goes through this cross area, which let's normalize this to 1, okay? And when it hits the surface, you can see, since the light ray is not perfectly into the surface, there's going to be a little bit of projection of, the light ray. Watch out, this is the cross section, CS, and this is the projected cross section, projected PCS. PCS is going to be bigger in this case than CS, and as the light ray goes, even more at a glancing angle, right? You can see that PCS, this is a huge difference. And the amount of photons is always the same in the same cross section, right? But since the amount of photons has landed on the surface area, I mean, the same amount of photons with the same amount of cross sections, so the same photon density that's traveling through the light ray, it hits a bigger area, meaning that there will be less photon hitting the surface per area compared to the cross section in the light ray. And turned out you can compute this ratio with a parallelogram, or you can just do some trigonometry here, right? And turn out this area, the density, say we make an angle of, let me define the angle theta here. So the angle theta is going to be, say the light ray is, okay, let's use this light ray as an example. The light ray is coming in this way, right? This is the light ray direction, and this is the incidence line. So this is going to be, perfectly, it's going to be 90 degrees of angle. And the theta will be the angle between whatever incoming direction is, or whatever incoming direction makes with the incidence line. So let's say that turned out the density, we have a normalized 1, or, in this case, let's just call it density here. The projected density has, density times cosine of theta, if you do the trigonometry. So if theta is 0, which means the light ray hits head on, cosine of 0 is equal to 1, so it's just the same density. And if light ray hits, at the perfect glancing angle, that means kind of it's projecting all throughout the surface, which means, at the glancing angle, the angle is going to be 9 degrees, cosine of 9 degrees is 0, so, if you extend out infinitely far, there's going to be, density is really 0. But if it's in between, then cosine is going to be some value that's lower than 1. I mean, lower than 1, yeah. So it's going to be a fractional number, so the projected density really is a fraction of the density. And this is how we get the directionality of light. The effect of the directionality of light. Since, different amount of energy will be absorbed per area. Right? Per area is very different, a very important concept, because what we want to do is collect the power per area. That's directly correlated to the percepted intensity of light. Again, the same, let me re-emphasize this. The reason we see light at different intensity at different angle of interaction is because the amount of photon per area changes. The photons itself do not change in numbers. What changes is the area of the projected area of the light ray. And that is why, we need to add a cosine term. Of course, we're dealing with all kinds of surface here. So, this incidence, how do we get this angle anyways? Well, there's something called a normal vector. A normal vector is the vector that's pointing outward, the most outward vector that's pointing out of the surface. Alright, I should mention, if light ray comes in underneath the surface, then the angle is going to be bigger than 0, which means there's going to be a negative value, which doesn't make any sense, so you probably want to clamp it. Let's just draw a line above it to denote that this cosine is really clamped between 0 and 1, because that's the only range where it makes sense in this context. So for a surface, if we can obtain a normal vector, we have incoming. Well, normally, what people do is, get the inverse of the incoming sun direction and call it L, then, you know, if we normalize both these two vectors, the dot product between n and L is going to be the magnitude of n times the magnitude of L, then, you know, multiply by cosine of theta that's making in between them, which is going to reduce to cosine of theta because the magnitude of both unit vectors are 1. So it turned out we can just use, you know, the normal vector dot with the light direction, the inverse light direction, to find, you know, the proportional intensity that from the sunlight. The proportion of intensity, the fraction of the max intensity on the surface that's possible. Okay. So in order to shade a point, we need to know the normal on that point, and we need to know the incoming light direction. Why don't we just go ahead and do that? The normal is going to be a little convoluted, right? So let's scratch that, actually. Let's just do, say the surface is perfectly absorptive of all colors, so it's 1. Right, one more thing I should take note of is the only reason you see things in different colors is because surface or matter, in this case, absorb light at different frequencies, and we're encoding color in RGB, but red, green, blue are really different frequencies of light that people see. So if a sunlight is perfectly, you know, white, say, and it hits some surface, and the surface, you know, say it's an orange, or even better, it's an apple, so it's completely red. Say it's a completely red apple. What that means is going to absorb. So the color has 3 components, or approximation. In real world, it's frequency of light. So the apple is red to human perceptions because when light enters the apple and scatters around and reflected out, it absorbed the entire green channel, it absorbed the entire blue channel, and only leave the red light, you know, leave it alive. So when the light, same light gets scattered around the surface with, you know, all these frequencies absorbed, but the red channel seems, you know, that the frequency that's associated with the red color doesn't get affected, and therefore when it's finally reflected out of the surface, you know, in all directions, we see red because that's all the frequency that's left in the light ray that's reflected to our eyes. So a good way to approximate is we can represent the color of the material to be a 3D vector and the incoming light color as a 3D vector, and we can multiply these 2 lights. So we basically, you know, by the way, for Apple, let's use the same example, the albedo, which is, you know, the absorption ratio, I mean, the absorption coefficient of the surface of the material is going to be 100, meaning that it's really the inverse of this, you know, if you want to, you know, be more scientific with your reasoning or more straightforward. What this means is that it takes no red, it absorbs no red, it absorbs all of the green and it absorbs all of the blue. And the inverse of that, which is, you know, 1 subtract by all the other values. Oh, by the way, the material surface should never have any value outside of 0 and 1. If it's negative, it just straight up does not make sense, right? And if it's, you know, 1.2, that means it absorbs more than the entirety of the light, means it absorbs more than light, which doesn't really make sense, you know? So, or can encode it in another way, you know, this is usually called the albedo. Albedo of the surface of the apple is going to be 100, meaning that it's going to take all of red and blue, but it's going to leave, you know, red intact, meaning, and this can be some fractional number, by the way. So it just means it absorbs the fraction, it leaves the fraction of light untouched when it exits the surface. And beware also that each coefficient denotes, say if it's 0.5, that means when the light leaves the surface, 0.5 of the light still exists. So if your albedo is like 1.2, then 0, that doesn't really make sense because apparently the light reflected is going to have more energy than the light entered. at this certain frequency, you know. So in order to stay physically, usually stuff looks good when it's, you know, more physically based. So you don't want to do that kind of thing, you know. If the coefficient is above 1, you're basically making like an emissive surface that emits light in itself, which you want to model in a totally different way than just, you know, through diffuse shading. So you want to multiply albedo with, you know, the irradiance, which is, again, it's a fancy word. It's really irradiance is just, you know, power per area, I believe. You know, the important keyword is per area here. So really, it's the sunlight. Irradiance in this sense is the sunlight multiplied with, you know, the cosine of theta. That's how much the projected area is, because we're doing, you know, power per area. So we need that. That's kind of important. My pen is kind of scratched. You know, whatever. Yeah. So it's going to be albedo multiplied with the irradiance, where the irradiance is equal to sunlight multiplied with the cosine of theta, which is, you know, the projected radiance in a sense. Radiance is, you know, without per area. Actually, it's per area per solid angle. You know what? Just forget about that. Forget what I said. Okay. So we have, we can just assign the material's appearance by making out some albedo for sphere and plane, and your radiance is, we can make up a sunlight, the light value, and make up a direction of the sunlight of which is coming in. The only missing part is the normal of the surface, right? If we want to take an arbitrary point on the surface, I want to find this normal, how do we do it? Now keep in mind we're representing this, our surface in sine distance function, meaning that it's a function of three scalars. So just a function of one vector returns a scalar, which is the distance. So since it's the distance, which means that if point goes out directly out of the point on the surface, the value of this function increases the most when it moves along the normal of the vector, because it's pointing the most outward in a sense. So it's probably where you want to go, the direction you want to go if you want to increase your distance the fastest. Why is this important though? Alright, so you realize the values inside the sphere, and here if the sphere is represented by the distance function, are going to be negative. And just right above the surface is going to be, you know, very small positive values, and as it goes outward, it's going to be bigger and bigger positive values, because, you know, the distance is farther away as we evaluate the point. There's a concept in multivariable calculus, I believe, it's called the gradient. It's the gradient vector, and it's, you know, used specifically for these cases when a function has multiple inputs. I believe it's denoted as the, you know, the upside down triangle. So if I have with three inputs, the gradient of the function, what it does is it returns a vector that gives us the direction in which, if we go along that direction, then the output will increase the most, which is kind of what the normal is in this case, because if we go along the normal, we increase the distance the most because it's pointing the most outward, right? And the way you'll obtain is the partial, the first component is partial derivative of, you know, f, the function, with respect to the first component, so on. This is the gradient, which is how we're going to do, since we're representing a 3D function, this is guaranteed to give us the normal of the surface at which point that we're shading at. Right. All we have to feed into it is x, y, z. You know, this is not complete. So what this means, I'm being a little ambiguous with my notation here, so excuse me since I'm kind of out of touch with math as a whole subject. What I'm trying to say here is we're going to take the rate of function change. So partial derivative of f with respect to x, what this term means is if we move realize the gradient is not constant over all domain of the sign distance function. So meaning that the gradient changes at each location. So in order to get the gradient at a certain point, the point itself has to be some kind of input, right? What this means is that if we're evaluating the gradient at location x, y, and z, this term is what's the rate of change of the output function, and the function output, the rate of change of the function output with respect to x, meaning that if I move x by a certain amount, then the function is moved by this certain amount. So everything is per area. Let me just try to give a more straightforward illustration. So say this is 1, right? Say this is 1. Since we can move this to the other side and say x. Actually, 1 is a pretty bad example. Let me just change it to a 0.5. So this is 0.5. This means if we increase x by 1, then f is also going to increase, but at 0.5 the rate of which x is increasing. And this is not necessarily true, but it's true if the gradient stays the same over that domain of 1 that we're traversing. All right. So this is kind of the rate of change, but with respect to multiple inputs. So this derivative has multiple inputs that the function output depends on. The way we can obtain these values is either one by differentiating the equation with respect to the x, y, z independently, or we can take the approximation. The fancy name is central difference, I believe. Remember that the definition of a derivative is the rate of change along a certain value. So df dx, I think, is that means fx plus h. So there's a limit here, right? We have a limit h that's approaching 0. The f function, which is the function we're trying to differentiate, plus h minus f over x and over h. So this is kind of the canonical definition of a derivative. What this means is that by traversing h amount along the x line, the difference in the output over the amount that it travels. So that's the rate of change. And if h is approximately 0, then that means then this will give up. Of course, we cannot do it by 0, but this expression is trying to express the concept of not this. So we're trying to here we're doing a 1D function. So we're just taking the concept of the rate of change instantaneously at a point in a continuous function. So this idea can be applied independently in a partial derivative sense. Is that we can just move the point along. Say we want, let's go back to the vector, gradient vector example. Say we want this value, which is the function of change, the change of function moving along x-axis at a certain point. What's the rate of change of the function? Well, we can really do the same thing. We can move. Remember the point is the input to the SDF is a point. So point. We move the point along the x dimension by a very small amount to subtract. So we move the point along the x dimension by a very small amount. Take the SDF of it, subtract it by the SDF of the default point, which is result in the difference of the function output. So that's how much the function output changes by just moving the point to along the x dimension by that amount. Divide that by the amount it moved, so a very small amount. Let me just write this out formally so it's less confusing this way. So you want to get the partial derivative of sign distance function with respect to x, y, z. Not with the input of x, y, z with respect to x. we can approximate this by saying SDF, taking the SDF of P plus, we only move the X because we want to do it with respect to X. So epsilon, a very small amount, this is the, the result if we move the point along axis a little bit. And this is the original output. This is the difference in output if we move the point along that direction a little bit over the epsilon itself. So this is the approximate rate of change along x dimension at point P. All right. Now remember, if we do this for all the points, all the x's, so the gradient, notice that we're only calculating the partial derivative with respect to x, so we can do the same for y and z. So the gradient of SDF x, y, z can be computed this way. You can just compute it for each dimension and put it in their rightful spots, right? My pen is making a noise that's making me worried. Whatever. Yeah. So this is going to be the result of our calculation. But remember, we're going to use this factor as the norm of the surface, meaning that it better be unit length amount. So we kind of want to normalize this thing, right? Well, notice that we're dividing all of these things. If we were to really list out each component, we're all dividing by a common factor. We can really factor out this common factor outside of our gradient, and we normalize the whole thing. That's still going to be the same amount. But realize the process of normalization. I can add a 3 here or add a 4 here and then multiply by 4. It's still going to normalize the same thing because the magnitude of the current vector does not really matter, which is really what we're multiplying here. So we can just get rid of this term. We can just get rid of this, the division by epsilon step in itself, because we're going to normalize the thing after the working process anyways. So really what that leaves us is this expression over x dimension, y dimension, and z dimension. And this will give, and normalize this, and this will give us the approximated normal vector of the surface. One thing you have to note is that this works perfectly if our function is a signed distance function, but sometimes we're invariably going to end up with distance estimators or absolute distance function, which does not have the signed component in it. In those cases, to compute the normal of the surface is going to be a little bit tricky because you can accidentally step inside the surface and then somehow it's a bigger value, but it's really supposed to be smaller, and this will mess up the gradient computation we're doing. So what we want to do for these fake models is what we want to move the shaded point back towards the camera a little bit, to move it back a little bit and to do the approximation, so that makes sure in each sample that we take for approximating the rate of change, they're all outside of the surface. That way it's more accurate, So it's, we got to be careful when you do computations like these, approximations like this. So why don't we start off by computing the normal of the scene, all right? So write a routine for that. So it's going to be a vec 3, right? So SDF underscore normal denoting, and we're taking the normal of SDF at a certain location, so it's going to be point P. Let's just say res, short for result. I'm going to return res. We're going to do this for each of its components. It's going to, just do the approximation. Then res is going to be, we're going to return the normalized value of results, which is the gradient that we have, a scaled gradient by epsilon amount because we're ignoring the division component of it. So it's going to be, like I said, refer back to the equation that we both derived. It's going to be, just this expression, okay? So it's going to be SDF P plus a very small amount, along the x direction. 0.001. That's pretty good. That's a pretty good approximation. Take that function. Wait, why do I have two SDF here? My bad. So SDF, this point subtracted by SDF of the point itself. This is kind of the floor differentiation. Another way we can do this is try to subtract the same amount along that direction. Usually the result of that is more accurate than what we're doing here. But floor differentiation is just fine in this case. Alright, that's the result, which, okay. It needs material, and we don't really need it. So I'm just going to put int ignored here. We're just going to pass in the argument anyways to place the compiler. I don't know if GLS has optional arguments, but I do this all the time because I really don't want to finesse with the spec of GLSL. It varies. NVIDIA cards add the extensions to these spec, and you can never expect which is good and which is wrong. So you want to always go with the same place approach instead of trying to be fancy. All right. So, okay, our screen just turned black. Okay, interesting. What? Oh. Somehow that did not give me a compiler. See that? Somehow this did not give me a compiler because, okay, that's actually justified because it understands it as I'm redeclaring the color and outer color is still 0. Why the program is, poorly designed or compiler is poorly designed, it should have given me an error or a warning at least. All right. So we have the routine to get the normal of the sign distance function. Remember our shading routine, right? So let's make up some light direction. L, it usually denotes the opposite of direction, some direction. This is so it's convenient when we try to do a dot product, since they're both pointing outward from the surface instead of some pointing in. You don't have to do negation and all that. Usually it's very convenient, and we want it to be a normalized vector. We can just kind of make up a light direction. So let's say the light is on our right side, and it's up also, and it's kind of behind us, like the sun is behind us, so it's the light is kind of pointing backwards. I mean, L is kind of pointing backwards, so it's going to be 0.9 or something. All right, so that's a light vector. We need the normal vector, which is SDF n of the point we have, which is just back to the array parameterization. Okay, excuse me. And at the rate at which the light is coming in, it's kind of all right. The light color. Let's take up the sunlight first. So the sunlight is just going to be perfectly white. All right. And the amount of irradiance, like I said, is going to be the sunlight multiplied by the ratio at which the projected ratio at which the light hits the surface. So it's the photon per area. It's really photon per second per area, but let's just say it's photon per area. So it's really that. So remember how we compute it. We just take the cosine of the angle, which neatly can be computed by just the dot product between L and N. And it's sort of by design. Projected ratio is dot L N, and keep in mind that it could possibly be, negative value, which doesn't make any sense if we shade the back face bit. Projected ratio. So we do a max by 0. What this means is going to take the max value between the first argument and the second argument. If the second argument, which is a dot, is between 0 and 1, it's always going to take this one because this is going to be the maximum value between these two values anyways. But if it goes into negative, then it's going to take 0, which means effectively we're clamping the result of the dot product. All right, so irradiance, we want some kind of albedo. Let's say the albedo is 1 for now. And remember, we just multiply albedo by irradiance. Right? And suddenly our scene is a lot more realistic this way. And you kind of experiment with where the light is coming from. It's going to look different depending on what the direction of the light is. And we can change our albedo based on the material index that's got sent back, right? So we can have some fun with that. So let's do this. The material lookup. If material index is 0, I already forgot what 0 stands for. Probably the sphere. I mean the plane. So plane could be just white. Okay. Else, if material is something else, if it's a sphere, then we're gonna make it red. Looks kind of hideous. Let's just try a different color. Okay. Some worse somehow. Let's just do white. Just do pink and give 4 different colors as well. Yikes, this is so nasty to look at. You know what? I'm just gonna keep the albedo to be 1. At least this looks kind of good. Of course, there's something wrong with what we're doing because light really bounces off the surface, and the bounced light will also create an increase in the portion of light. I can demonstrate that well. And there's sunlight as well. I mean, the skylight as well, but we don't really have sky, so this is kind of looking at the moon's surface in a sense. But yeah, this is the basics of shading, and I don't want to go too long on this. There's a lot more things we can do, which is approximating the skylight, get some ambient occlusion in this thing. Or, do a fog. Which is also good. But since this video is just going to be about shading and it has, I've pumped a lot of material into your head, I think I'm just going to stop here. And yeah, this is the basics of shading. And I'll see you in the next video.